Alright, so hello and welcome to this video tutorial for RC Hibbeler's Engineering Mechanics Statics textbook. So we have this problem from chapter 3 here, which is asking, determine the magnitude of forces F1, F2, F3, so that the particle is held in equilibrium. Now, what's interesting or maybe slightly new to you guys about this problem is that the particle is, or the diagram here is in 3D space, right? We have an X, Y, and we also have a Z now. What I find interesting about this problem is that one force is not like the rest, right? So F2 and this 600 Newton force here are just acting in the X. This 900 Newton force is just acting in the Z. This F1 here is acting in 2 dimensions. It's acting with a Y and a Z component here. F3 is the one that interests me the most because it's acting in all 3 dimensions, right? It's acting in the X, the Y, and the Z. Now, breaking this down into its constituent components is a little bit confusing maybe at first, but let's try and break this down. So basically, ask yourself, what is the Z component of F3? Well, looking at our diagram, I'm going to trust that you guys understand that we could say, well, the Z component is 4/5 of F3. The idea being that for every 5 it acts in the direction it's acting, it acts 4 in the Z direction. What is its X component then? Well, we can't really, unlike with 2D problems before, we can't just say, well, it's 3/5 of F3. That's just not true in this case. I've drawn a little diagram on the right-hand side here. So we get this idea that this, if this hypotenuse is our F3 here, then this is our Fz in this context, which we can also say is equal to 4/5 of F3. This bottom component here is what we can describe as its XY component. Okay, it's not the X component, it's not the Y component, it's the XY component. So that is describing how much F3 is acting in the XY plane. Okay, and as you can probably infer, that is equal to 3/5 of F3. Okay, so we've hopefully got one step closer into breaking this down into its constituent components. This is where we can kind of introduce this idea on the XY plane down here. So we can almost treat this line here as our F3, XY, right? It's the XY component of F3 here. And we can kind of replicate this diagram that I've drawn on the right-hand side here. Let's just go ahead and do that. So if this hypotenuse is kind of describing F3, XY here, then this vertical is kind of describing the Y component of F3, right? So we could call this F3, Y, which we note here is equal to 4/5 of F3, XY. And our horizontal here we can say is F3, X, which is equal to 3/5 of F3, XY. Okay, so I've done that just to help us understand how we can break down these kind of 3-dimensional vectors into their constituent components. Let's go ahead and solve this system then. So just like you guys are hopefully used to at this stage, if this is in equilibrium, then we're basically saying if we add all the forces up together in the X or in the Y or in the Z, they will sum to 0. So let's go ahead and start in the X. Why not? We can say the sum of forces in the X are equal to 0. Therefore, things acting kind of this way in the X are equal to things acting kind of that way in the X. So things acting kind of towards us this way. Evidently, we've got this 600 Newton force, so we've got that. We'll also have the X component of our F3 here acting this way towards us in the X. And we can note that this is equal to 3/5 of F3, XY. And we also note that F3, XY, I could add some 3's in here, is equal to 3/5 of F3. So the x component of F3, having done what we've done earlier, we could describe as 3/5 of 3/5 of F3. Okay, so since this is 3/5 of F3 comma xy, and F3 comma xy is 3/5 of F3. I hope that makes sense. So that's acting kind of towards us. What's acting against us in the x? We've got F2. Okay, is this solvable? No, because we've got two unknowns in there and just one equation as of now. Let's go ahead then and resolve in the y. So we can say forces in the y sum to 0. Therefore, things acting that way in the y are equal to things acting that way in the y, right? What have we got acting this way in the y? We have got presumably the y component of f1 here, which we could describe as 3/5 of f1. So, sorry, not 3/5, 4/5 of f1. Okay, so we've got that kind of acting towards us in the y. What have we got acting against us here? Well, we've got the y component of f3 here, right? Now, we could describe that as 4/5 of f3 comma xy. And we know, again, that f3 comma xy is 3/5 of f3. So we could say this 4/5 of f1 is equal to 4/5 of 3/5 of f3. Okay. Now, are we in a solvable place yet? No. The reason why is because we've got three unknowns, f1, f2, and f3. And we've only got two equations. So we've got 1 degree of freedom there. We need to keep on going with this. So let's go ahead and resolve in the z. So we can say forces acting in the z sum to 0. What have we got acting down? Well, we've got that 900-pound force acting down, right? We've got, what have we got acting up? Well, we've got the z component of f1, which we can describe as 3/5 of f1. And what have we got? We've also got the z component of f3, which we described earlier as 4/5 of f3, right? So we could say plus 4/5 of f3. Do we have a solvable set of relations now? Yes, we've got 1, 2, 3 unknowns, right? F1, F2, and F3. And we've got 1, 2, 3 independent relations there. So we've got 0 degrees of freedom. We can go ahead and solve this problem. How would I approach this problem? We could look for places to simplify our equations here. And one thing that I've noticed is in our second equation here, we can divide both sides by 4/5. We can effectively cancel 4/5 out here. So if we eliminate them, we are left with this idea f1 is equal to 3/5 of f3. Now, this is a very convenient idea, right? When we have one unknown is equal to this in terms of another unknown, that's very helpful for substitution. We could take this and we can substitute it into our third equation here. So we have f1 in terms of f3. We can rewrite our third equation. We can say 900 then is equal to 3/5 of 3/5 of f3 plus 4/5 of f3. I reckon it would make sense to simplify our right-hand side and then to factorize it. So we just have f3 there, which we can then make the subject. So let's go ahead and do that. We can say 900 is equal to 3/5 of 3/5. That is 9/25. We can kind of do two steps in one, really. So I've simplified this 3/5 of 3/5 down to 9/25. I've taken that 4/5 and I'm going to carry out a factorization all in one. Okay, so we're left with this idea here. We can therefore say that f3 is equal to 900 divided by 9/25 plus 4/5. Okay. Now, when we take this 900 over 9/25 plus 4/5 and bung it in our calculator, we find that f3 is equal to roughly 775.5 5.9 newtons. Okay, so we've got our F3 there. We're in a good place with this problem already. We can substitute that into this idea here, since this is a very convenient equation. We can say therefore F1 is equal to 3/5 of 775.9, which when we bung in our calculator gets us a value of 465.5. Okay, so we have our F3, we have our F1. The only thing left to solve for is our F2 here. What we could do is we could take our value for F3 and substitute it into this first equation here. So we can say, therefore, F2 is equal to 600 plus, let's just call it 9/25 of F3, which is 775.9, which gives us a value of 879.3 here. Okay, so these are our solutions. If you have any questions or comments about that problem, please feel free to leave them down in the comment section down below. Otherwise, thank you very much for watching.